tonight or prefer to watch it later on their own time? All right, so fingers crossed on that. I tested it out earlier, so hopefully it should work out. All right, so thanks for joining us tonight, those of you who are here. I'm just going to go over what we covered in the first half of lectures for the course to prep for this midterm review. So we'll go over a few things tonight on the agenda. The first will be the exam structure, which I think Paul covered in class, but we'll just go over that one more time and give people an opportunity to ask any questions that they didn't think of in the last lecture. We'll talk a little bit about, we'll go over all of the lecture content that's going to be covered on the midterm. We'll talk a little bit about common pitfalls that we've seen on these exams in the past. So kind of the little things that people tend to miss on the exams, and also some tips for how to navigate the exam successfully. And then at the end, we'll talk, this is something I didn't do last time, but something I'm going to try out this time around is just a section on practical application and conventions. This is just more of a in the real world Python coding. This is the kind of stuff that you'll see often, or these are things to do or not do. So there's just kind of lightweight curios at the end of the discussion today. And then we'll wrap up with questions and an open discussion if people want to try if people want to ask questions about what would happen if we did this, or what does this block of code do, then we can definitely dive into that. And as I mentioned on the Slack group, if you have questions, maybe the most efficient way to ask questions would be to just go over to that midterm review channel on Slack and ask those there, but also feel free to dive in here and just ask the question out loud is totally fine too. All right, so first off, let's dive into the exam structure. Oh yeah, and if connections fail or you or my voice cuts out or anything, please don't hesitate to let me know, and we'll try to get that resolved as soon as possible. But exam structure. So as Paul mentioned before, there's going to be multiple sections to the exam. There's going to be multiple choice, and that includes either choosing one answer or choosing several answers if they're all correct answers. And there may be, that classic final answer at the end of the multiple choice, which is all of the above or none of the above. Just to cover all of our bases there. Following that, there will be a short answer section, and just a couple recommendations here is to, if you feel like you're getting stuck, to be transparent about your thought process. Explain why you're saying what you're saying. Explain where you got stuck, so that at least will tell us how far along you got. But it's definitely better to be, to a certain degree, it's better to be more verbose there than less verbose, and just give us more information to grade with if you feel like you're really stuck on something. But at the same time, if you do know the parts that you do know what's going on, be precise and succinct. So when you know what's going on, write it out as you know it. And then there will also be a coding section where we'll ask you to code up a function or class or what have you. And in that section, it's best to make indentation clear, because that's definitely critical for Python syntax. But don't fret if, it doesn't need to be an exact quarter inch, to make sure that you get a good grade on it. It just needs to be relatively clear so we understand that you get the syntax of the code. And also a recommendation I have is because we're not using a text editor, and we're very used to using text editors where we're free to write out a bunch of code and remove it and hack it apart, and that won't clutter up our page like it will on the exam. It's really best to sketch out the code first lightly. So even just things like, okay, the problem's asked me to write a function, so I'm going to write out that function and then just figure out what the arguments of that function are, and that'll be it. Or maybe an even better example is if we're asking you to write a class definition, you'll simply write out the class. At the top of the page, you'll say class, whatever the class name is, and then you'll have a section for each of the methods, and you'll fill those in accordingly. But try not to get into a situation where you're trying to write all this out the first time successfully, because that can be very difficult, as we all know. And that'll just kind of create clutter and make it difficult for both you to navigate and us to grade later on. So yeah, also be able to interpret code. That's going to be part of the exam for sure, and we'll talk about that a little later in pitfalls. The full list of topics is linked here in the slides, and I believe Paul provided one as well in the last lecture. So before we move on, are there any questions on that? I'll just wait a few seconds here. Okay, all right, sweet. So we're going to go ahead and move on, and we'll start covering some of the lecture material. So starting with just the basics, we'll just talk about our REPL, or the ordering of how Python interprets your code. Right? So Python is this system in which, rather than creating compiled code where before we even run the simulation, the computer can understand the order of operations that it's going to take, Python interprets on the fly how it's going to act. So, and that occurs in this loop, which is essentially, it's going to read through the code that you've asked it to execute. It will then evaluate that code if it finds it to be valid in Python. It will then provide any output that's a result of that code, whether that be a return value or a print to screen. And then it's going to do that again for the next statement in Python. So nice to remember the ordering of that in case we get into any details on that on the quiz or on the test. And to remember kind of that variables are really just a name assigned to a value or to an expression. We talked about this in a fair amount of detail in lecture 3, that you can assign functions to a name and then use them later on with a completely different name. A similar way to think of it is as an alias for something else. So here, f is just this alias for the lambda function defined below. Really important, I think, in general in Python is to know what to expect when you assign a variable or name. So here we're looking at this example where we assign the value 6.0, this floating point value, to x, and then we assign y to x. And below, we're assigning x to that explicit value, and then y to that explicit value as well. And so it's really important here to know what the difference is, and equally important, I would say, is to know how can we check this and verify that we have the right idea. Normally this is a question that I would kind of pose to the group if we were doing this live, but we'll just flip over to the notebook that we'll be looking at today, and we'll just look at it as we go. So in the example above, I said that we have this floating point value, 6.0, and then y is equal to x. So if we execute that, and then let's do another one. So we'll say a is equal to 6.0, and b is equal to 6.0 as well. So let's go ahead and execute that, and we'll make a new cell. So now we have these values in our notebook, and if we look at these, the main difference here that we want to be able to identify when it comes time for the exam is that in this case, if we look at the output of whether or not y is equal to x, as we expect, we get the answer that those are in fact equal. Whereas if we check to see if x is in fact the same as y, that's also true. Because we have assigned, through this naming, we've said that x is equal to 6.0, and we said that y is equal to x, and so they're the same. And so that makes a lot of sense in the terms of reading that in plain English in Python. But if we look at that for the second example, we'll see that a is equal to b, and that is true. So okay, good. 6.0 is equal to 6.0, but if we look at a is b, we find that that's false, which can be a little bit confusing, but we need to remember that the equivalent of doing a is b is looking at the ID of a and the ID of b to see if those objects are actually equivalent. I'll print both of these so we can see the output of both lines real quick. But the equivalent here is that we're looking at whether or not those are the same objects in memory space. And so tracking that in terms of a single floating point value, while it may seem relatively trivial, it becomes much more complicated when we get to nested data structures and things like that, and understanding what parts of the data structure are we copying, what parts are we not. And we can dive into that a little bit more down here. So we look at this block, we see that we're doing the same thing, but with a list. And we see the same thing is true. So we have some list is just equal to a list containing this one string that is just one, and then we assign the name, and then below we do the same thing. So this also applies to data structures. That's kind of the point here. And then we'll kind of get into later on a little bit. We'll get into whether or not. Well, let's just look at it now. So let's make yet another list is going to be a list of some lists. So this is essentially, or really, let's just go ahead and we'll do this properly. We're going to make a copy of that list. So we'll import the copy capability from the standard library. And then we're going to create a copy of some list. And then we'll say, we'll look at these same kind of equivalent evaluators or equals operators above. Is that equal to the list that we copied? Some list. And if we look at that, our final print statement here is true, meaning that yes, they're equal. And we've made a copy, so if we look at is yet another list, is that the same object in memory? We find that that's false. So this is very similar to the floating point situation that we were looking at before, and also these couple of examples. But it becomes a little more complicated when we do something, when we look at something like this. So let's check to see if the first entry of that list is the same as the first entry of the other list in memory. And we find that that's actually true. So even though we've created a copy of the container, the objects within that container were not copied. And we'll remember from lecture that this is the difference between a deep copy and a shallow copy. So that's definitely something to keep track of. So we've covered those things. So when we're looking at these different styles of creating values and tracking them in Python, in the first example versus the second example, what is the difference? So the first one, we have essentially a value that's been aliased under several different names in our namespace in Python. In the second case, we actually create two different objects with the same value. And we can test that using the ID or the is comparator. All right, so some detail about native types in Python. Ints have unlimited precision. So the larger the int, the more memory it's going to assign in Python to represent that accurately, whereas floating point values have approximately 15 digits of precision. Complex values, probably the most important thing to know at this point in Python is that they're pretty rarely used. And strings as well are another native type that use this UTF-8 encoding. It's probably important to understand what encoding versus decoding these means, so that whether or not we're looking at these things as character values when we iterate through a string, or if we're looking at them as bytes. And they are also indexable. Strings are also indexable and sliceable, just like containers in Python. Booleans, I think we're all fairly familiar with those at this point. And maybe an important thing to know about those is that as you're checking them within As you're checking different types inside of an if condition, other types can be implicitly cast to Boolean types inside of if statements. So native types. Another detail to get into is similar to the one that we were looking at above, is kind of this, and this could maybe even go in the practical application section, but it's important to understand as well in terms of fundamentally understanding the Python implementation, is whether or not we should be checking equals equals none or is none. Again, this is a question that I would typically pose live, but let's dive into it in the notebook. Oh, not that notebook. This one. So, similar to before, where we were looking at different containers or values and trying to decide whether or not we're looking at their equivalence, meaning like, will we get the same value out of these objects, or are they the same actual object in memory? In Python, there is only one none. And so when we're looking at comparing whether or not an object is equal to none or is none, it's really best to say, is it actually the none object? Because there is only one of them, and so while 90% of the time you're going to get the same result in doing either of those, it's really better, I should say, to just compare them directly. Because if you ever say that something is equal to none, you are actually getting the same object. Right, so Boolean operators as well, that kind of dives into that in a different manner. If we look at what these different objects are that we've looked at, we have this employee, John Smith, and that employee has some data associated with it as an attribute, and we have an employee Smith. So these could have been two different objects that were created in Python, and they may both have attributes of data, but we don't really know where they originated from. So employee John Smith could have been aliased as employee Smith and created with a different name, and they're both pointing to the same object. Or it could be been created completely independently from different data sets, and we want to compare these two things. And so a couple of things are important to remember here. Again, that if we use is here, we can check to see if these are actually the same, are different names for the same object. But another thing that's important to remember from our lecture on classes is that if we use this equals equals, then this class structure might have its own unique implementation of deciding whether or not objects are equivalent. So for example here, these objects may not care whether or not the first or last name are the same inside of these data objects. One says Jonathan and the other says John. But maybe the only thing that they're comparing on is these ID values. So while we have different data as part of the class, the equals, our equivalence operator here is going to only check one of these values and determine that yes, in fact, these two objects are equal. So it's important to understand. I think for native types it's pretty straightforward, but for classes, just recognize that this operator could be implemented in different ways. All right, and then diving into some of the collections and data structures that we've looked at before. We have the list, the tuple, the set, and the dictionary. And remember that the list is kind of indicated by these square brackets. The tuple is indicated by the parentheses, except in the case where you're using a comprehension, where the parentheses comprehension like this is going to create you a generator. So let's just remember that. That's kind of that one corner case where if you're defining a set versus a generator, so I'll make a set here instead, and it's just going to be these two things. But if I look at the type of the of the generator that I created above, or what I claim is a generator, and the set that I've created below, we'll see that in a tuple, I was saying set. The parentheses are a tuple, my bad. In the case above, we see if we use this comprehension, we actually get a generator that's going to use lazy evaluation and to give you the next value in a set of in a sequence of values. And then below, if we define this explicitly, saying 1, 2, 3, and we look at the type, it's going to give you a tuple, not a set. Apologies for that. So the set, however, just so we put all these examples together, is going to have these curly brackets. And if we put items into that set, which can be of multiple different types, then we'll see that come out as a set. And then finally we have the dictionary, which if we wanted to find one of those, it'll look something like this, where we'll use curly braces, but here we use a colon to separate the values on the left-hand side from the keys on the left-hand side from the values on the right-hand side. And so we see that is a dictionary in that case. All right. And here I'll make a plug also for the default dictionary, which I talked a little bit about during one of the coding review sessions. It's really handy if you're trying to populate a dictionary where you may not have entered a key before. The default dictionary will automatically populate values for you, and I'd highly look into its use at some point. Okay, lists. So now we'll kind of go through these in detail. So the literal syntax, like we talked about before, we use these square brackets. And here's its basic comprehension syntax, where we use this L for L in capital L inside of this brackets. Lists are mutable, and so they can grow and shrink as needed via some of the methods that we see here below. So we can append to lists, we can insert things into lists at a certain index, we can reverse lists, we can pop items off of them, and we can sort them. In is used to test membership, so rather than writing some kind of for loop, we can just write one single statement asking something like, if we have a list, is if something like this, if 1 is in our list, print it's there. And so we see that come out at the end. Again, as I mentioned before, they're mutable and they're also ordered, meaning that if you iterate over a list and you haven't modified it between iterations, then you will get items in the same order as you did before. Tuples are literal syntax, so these parentheses. So we can place items into that. And as I mentioned also earlier, their basic comprehension syntax is not a thing. If you use the comprehension syntax for tuples, you'll get a generator. So indexing works the same as lists, and you can get the length with lane is probably the most notable thing to say about them. They are immutable. So once you've created a tuple, in this case here, once we've executed this line, this tuple will be unique. We can copy it, but we cannot change that particular object in memory at that point. And they are also ordered in the same way that lists are, if you iterate over them. And here we have sets with their literal syntax, and they do have a comprehension syntax, so you can turn a list into a set. It's really handy if you have a list of things and you want to get all of the unique items inside of that list. If you put them into a set, then you know you'll only have one entry for each unique item. They're also extremely fast for containment checks. So in the same syntax that we use for a list, if we look for our value, so if A is in our name S, we'll also print it's in the set. So we can use that same syntax to check that things are in the set, but it is considerably faster than if you do that for a list. It is a mutable object, and so it has methods like add. You can also do comparisons of different lists in very effective ways. We saw that in one of the homework assignments, where you can take the difference of these things, the intersection, so all the values that are in both lists, and the union, all the values in, all of the intersection is all of the values that exist in both sets, and the union is all of them from both sets. You can also use these infix operators in place of these operations to get from this more verbose sort of syntax to do something like an intersection here with the straight up and down slash, or the ampersand here. You can do subtractions, etc., etc. These are mutable, and they are technically unordered. So as you enter items into a set and iterate over them, they're not necessarily going to come out in the same order that you put them in.
I have a question.
Yeah.
So in the difference method, does it get like the symmetric difference, or is it like set minus?
It is like set minus.
Okay. Thank you.
Sure. All right, our other containers here, we have dictionaries. So we looked at the literal syntax for that. Again, keys on the left-hand side, values on the right-hand side of these colons. And it also has a comprehension syntax. So we can do things like this, where we have a list of keys and a list of values that we want to enter into a dictionary. So we can zip those together and loop over them, and then enter them into the dictionary as key and value. And uses these key value pairs, which I think we're all familiar with, and can look up things using a given key rather than an index. They are iterable though, and it's important to know here for dictionaries what you're going to get when you iterate over them in different ways. If you iterate over a dictionary using only the dictionary, so in a syntax something like this, or let's just say for I in our dictionary D, let's print out what I is. We're going to see that we get one value from that. And let's actually do this in a different cell, just so it's less cluttered in the output. For I in D, let's print I. So we see here that we just get one value coming out, and that's A. So if we use this syntax, we're only going to be looping over the keys of that dictionary. Whereas if we iterate over the values, then we see we're going to get 1, which is this value here, the only current value in our dictionary. And if we use items, which is maybe one of the most common ways that these are iterated over, we will get a tuple for each iteration of the dictionary, where we have our value is the first entry, our key is the first entry, and our value is the second. And that's typically in the same way that we created that dictionary in the slide. Those things are typically captured here in the for loop by unpacking that tuple kind of as we go. And then those can be operated on like so. Dictionaries are also mutable, and they're also unordered. So as soon as you've added, in between iterations, if you add or change values and keys in the dictionary, you will not necessarily get the same iteration as you did before. Here we kind of covered this a little bit in the notebook, but iteration directly on it will iterate over the keys. You can use values to get the values, or items to get the items. I mentioned before that certain objects have implicit Boolean conversions, so empty containers. So any of the containers, if they contain no objects and they are placed into an if statement, will implicitly convert to false. So for a concrete example of what that means is something like this here. So A, here we create an empty set, and if we just simply evaluate A as a Boolean to determine whether or not it's true or false, and we run that cell, then we see it is in fact false. However, if we add something to it before we do that evaluation, or insert, sorry, nope. Okay, let's just put it in the literal. Sorry, I can't remember the method name for some reason right now. But yeah, so if we drop that into the set, we then no longer have an empty set when we evaluate this conditional, and we get that A is in fact true. Okay, so we've covered a lot about containers, and I'm just going to go through kind of an exercise that I think is helpful for making decisions about what data structure you're going to use, especially in a situation like an exam where you have to make these decisions on the fly and you don't get like a lot of time to just like try to execute the code and see how it works. So it's useful to be able to see things, to see data that you need to create containers for and understand like what's probably the best data structure to use for this. So the first example we have here is a DNA sequence fragment, and so this is just a set of different characters coming in that represent this DNA string. And what data structure should we be using for that? That's pretty straightforward, I think, right? That these are all characters, they're in a sequence, we want to maintain that sequence, and string checks pretty much all those boxes. We could put each of these characters into a list, but that's probably a little bit overkill. The other thing about a string is that we probably don't want to be changing this DNA sequence, causing any mutations in it, if you will. So the string being an immutable object will kind of keep us from doing that as well. Another set of data we have here is a set of many sets of 3 values representing different colors. And so we have these 3 values ranging anywhere from 0 to 255, and they represent the red, green, blue values. And because these are fixed colors, probably the best thing for us to be using here would be some kind of tuple. We don't want to put these into a list because we know that this is always a fixed length set of data. It's red, green, and blue. We're not going to be adding anything else to it. So tuples are probably the way to go in that case. Here we maybe have some data that we're trying to translate into a color library. So here we have a first entry, which is going to indicate our color name, and then the next 3 values will indicate the red, green, blue value of that color in the library. So here, if we kind of pull this apart, we see like, all right, well, pieces of this we did before as tuples, so let's go ahead and do that. And then we need to associate our tuple with this color somehow. So we could definitely like do tuples of tuples and put those into a list, and then if we wanted to get something out of that color library, then we would iterate over the colors or check to see if that specific tuple was inside of our list. But that's kind of verbose to have to type that out to check to see. Like we'd have to type out white 255 255 255 to see if that's in our library. So maybe it'd be better if we did something like a dictionary where we had the key being the name of the color and then the value being the tuples. So then it becomes a little bit more readable. If we actually want to look up a value in that dictionary, we just pass it the key white, and it's going to give us out all the information that we need to represent that color. So yeah, that pretty much covers containers. We'll get into iteration. So I'm just going to pause for a brief second and check Slack to see if there's been any questions. And if you have any on the Hangout, please dive in. All right, cool. Glad to hear it's going well. Right, so we talked about a few of these different types already, but sliceable built-in types that we've dealt with are strings, lists, and tuples, where our slicing syntax looks like so. When we're accessing an object, we'll place these brackets after it. The beginning point is our starting index. The second one is our non-inclusive stopping index. And we also have a step, so we can iterate over values in jumps of 2, or one after another is the default, where we have this default step of 1. The default stop, if we do not provide a stopping point, is going to be the end of the iterable, meaning that, as discussed before, it will get to the point where it returns that stop iteration, and then we'll understand that we are at the end. Again, this is, or for these types that we've discussed above, for these native Python types, this is all true. But if you're dealing with objects that are not of those types, they may iterate over data differently. And so it's important to understand that as you encounter those kind of objects. We've covered logical blocks for sure, where we have this kind of syntax, where we'll have a if statement and a condition, and then we'll have a bunch of statements if that condition is true. We'll have a else if we want to do something different. If our first condition fails, we'll check that condition and run more statements, and then finally we can throw an else in here that will always happen if all of the other conditions are false. So I'm just going to page through here and see if there's anything else that we wanted to capture, but I think we're doing good so far. And if there's anything that you would like to see just try it out, or if you're curious about like what would happen if we did this in the notebook, feel free to dive in. A few different ways of running loops in Python. We have this while with a condition afterwards and then a bunch of statements, and it will continue to go through this loop as long as the condition that we evaluate here is true. And if any of the names representing objects in this condition are updated inside of the while loop, those will be reevaluated as that condition is checked. Here's probably our more common forms of loops. So we've already seen a couple examples of, but we can do for I in iterable and have a whole bunch of statements underneath there for executing something for each of these different iterative values of I. And here we can also unpack information coming out from an iterable. So we saw that in the form of key value pairs when we were iterating over dictionary items. And so that's a really useful way to avoid verbosity, where instead of having to say A is equal to the first item, B is equal to the second item, under here inside of the for loop, we can just do that in one step. These are pretty handy to know, especially just for knowledge of Python, but also just to make things a lot simpler. As essentially you can avoid getting stuck trying to figure out how to zip two lists together or writing 4 or 5 lines of code to do it in the exam by just putting this in here. And so this might be a good place to note that the standard Python library functions like these are definitely free game in the exam. We're not expecting you to implement anything like this in the exam unless it's specifically part of the problem statement. So this one's probably been used quite a bit, where we have range, which is just going to return ints going from n to m-1. So it's non-inclusive, again, just like slicing. It's non-inclusive, and that second value. And that is a generator object. Zip is going to tie two iterables together, returning a tuple with each entry, one from the first iterable and one from the second. And one thing to note about this is that if the iterable A is shorter than iterable B, it will only iterate as long as the shortest of the two items. So if A is shorter, it's only going to go through as many items there is in A, and it will stop, and you won't encounter any of the items in B. Another one that's really handy to know, often when you are searching for the index of something in an iterable, is this enumerate. So we can say enumerate over this iterable, and it's going to return along with each object in that container, it's going to return the index of that object in the container. So handy in that way, for sure. Oops. Just going to look through here. So yeah, this is just kind of our example again on generators using range. We'll put a little break in there, remembering that if we have a range that's going from where we don't give it a second value, it's going to go all the way up to the value that we give it. So here we're going from 0, we're getting 5 values starting at 0 and ending at 4. And in the second case, the same thing, but we've provided a starting value. So it's going to go from 0, it's going to give us, well, it's going to start at 0. It's going to give us 10 values, so it's going to go from 0 to 9. All right. Let's talk a little bit about defining functions, where our syntax here is just define. So Python's going to recognize this def keyword, and then the next thing that comes after that is the name of the function, followed by the arguments that are going into that function, wherein a whole bunch of statements could be executed and computation done, and then we will return output from that function. The default arguments in functions look like so. So very similar with the def, the function name, the arguments, and then following with a default argument that uses the syntax here. We use the equal sign, and then what the default value of that argument is going to be. And similar, we have statements inside with the return. Something that's really important to remember is that functions will always return something, even if it's a none thing. I really apologize, but sometimes bad jokes help you remember things, so why not try it? Yeah, so even if you don't have a return statement at the end of the function, if you call it, you will get the none type back from that. So if we look at an example down here, we'll just define a simple function. It's going to take in arguments, and it's just going to print the result of x times y. And we're going to actually capture, maybe we made a mistake here, and instead of thinking that this was printing, we thought that we define this function and it's going to return the multiplication of these values. So we're going to try to capture that as a result. Equals a of 3 and 6. That's going to print out 18. And then if we look at what result actually is, we find that, in fact, yes, none has been returned from that function. So just because we're not returning anything doesn't mean we don't get anything from that function. Methods for taking unlimited arguments into a function is the *arg syntax, which allows a function to take any number of positional arguments, not default arguments, positional arguments. So here we have this example of x times y, and we're going to take in *args, and we'll assume that the args passed into this function where is going to have a setup so that x is equal to the first argument, y is equal to the second. And then we'll return the multiplication of those two values. Keyword arguments take on this ** keyword args. And here we have this x times y. And in this case, instead, remember that keyword args is going to get us a dictionary of different key value pairs. And here we'll look up those values using keys inside of keyword args x and y. So to think of it in terms of this syntax where we have default arguments coming in, These are also sometimes called keyword arguments because we have a keyword and then the actual argument value. And those are what get basically packed up into a dictionary when we use the ** keyword args. And then the names or the keywords become the keys, and the right-hand side here become the values of that dictionary that's coming into the function. So here we have a function where we're going to pass in a set of star arguments, and we'll have a value that starts at 0. And for every argument in our set of arguments, we are going to take that value and we are going to add equals args to it and then return the value, right? So what happens if we do this here? Well, we get kind of weird behavior, right? So if we notice in this section above, I'll kind of reproduce this real quick. My function val equals 0. Return val. So we kind of intend this maybe to do something like take in a list of integers and let's print the output of my function, and let's see what we get here. Oh, right, sorry, I need to actually call the function. So we're going to pass it this list A, and when we call it, we see we actually get a type error. So we need to be careful, remembering that when we pass this in, args can be of any type. So if we look at what is happening here, we're going to look at what args actually is, just as a reminder of what that is coming into a function. And then we're going to also look at what the first value of args is. So if we look at this, we see that our star args is when they come into a function like this with that syntax, you're going to get a tuple, which is appropriate because when we pass arguments into a function, we don't really want them to be modified on the way into the function in some strange way. We want to make sure that that object is static. And then here we find that instead of looping over the list that we passed in, because args is actually a tuple, the first argument that we passed it is A. So if we index into arguments, then we actually see the list. And so at that point, we can then loop over our argument. Right. So I think this was actually the example I was going for. So if we loop over for arg and args, the first argument in args at this point is a list. So we get it in, we have this tuple, and then we start iterating over that tuple. And so the first thing we get back from this for loop, the first thing that arg is set to is a list. And so if we set val, and we try to add val, which is at that point an integer, to the list, then we're going to get this error, which is this unsupported type operand. So we need to be careful with that. And in this case, right, we want to make sure that either we can pass this list in so that it's already expanded, right? And so what we just did there was we kind of unpack this list as we pass it into the function. So this is the equivalent of handing in 1, 2, 3, 5, and 7 to this function, and we'll get the same thing. Or alternatively, we can pass in that list, but then we just need to understand that in the args, we want to access that first element so that we're iterating over the list that we intend to and get the output that we intend to. So args and keyword args can be a little bit tricky to keep track of, and definitely something that would be good to get some practice with. All right, so a little bit more on defining functions is scoping. So we have this leg B or LEGB kind of ordering in the way that Python tries to look up names inside of a function. So the first one is going to be local, which is at the function scope, meaning that's names that we have declared inside of the function. There's the enclosing scope, which is scope above the functions, or variables that have been created just above the function definition. And then we have the global scope, which is essentially the file scope. So that means that it's any of the names that we've declared that are unindented in the file that we're working in, if you want to think of it that way. So there's a very subtle distinction between our enclosing scope and our global scope that is actually quite important, because the enclosing scope can kind of change, right? So it can be at multiple different levels within the file, but there is only one global scope, which means that you're at the file level and have not indented any of those names, is how I tend to think of it. And then finally, there's the built-in namespace in Python that kind of comes with it. So all of these different built-in functions and types that we've been using. And I think there's one little corner case I just wanted to cover on scope that's kind of strange. So here's kind of a weird case for scope, and it kind of details the meaning of enclosing scope and how it can change before and after you define a function. So here we are going to define a function which is just going to print a variable, and that's all it does, is it prints a name variable. So here in this cell, we see that name does not exist, neither in the local scope nor the enclosing scope. And so underneath that, when we try to call it, we get this error coming out saying that it can't find that name, that it's not defined. However, without changing that function definition in the next cell, we will add that name to this cell. And at this point, when we print the variable, it works just fine, because even though we've already defined the function, because Python's an interpreted code, or an interpreted language, it's going to, when it evaluates this, it will try to do the enclosing scope name lookup for this variable. And so down here, it's going to find the variable in the enclosing scope and print it out just fine. So it's just something to keep in mind. There's some strange cases you can get into with that. Generators, we've covered a fair amount. They are objects that are intended for one-time use. Once they've been exhausted, they will raise a stop iteration. They're usable in for loops, or you can get the next value from the sequence in the generator using the built-in next function. It's really good for avoiding iteration over giant containers. So long lists or sets or tuples. Generators are really nice for defining a sequence without actually generating all of those sequence values up front. So it saves us a lot in memory. And remember that Python objects are very rich. Even integer types and floating point types are very rich in Python, meaning that they take up, while they're very expressive and you can do a lot with them, they take up a lot of memory as well. So it's particularly important in Python to avoid creating really giant containers of of values if you don't need to, and that's where generators can come in really handy. Their basic comprehension syntax kind of replaces the one for tuples, as I mentioned above, and looks like that. We've discussed exceptions as well. So the keywords here to remember is that we can raise these exceptions. We can try a set of code and then accept different exceptions coming out of that code. And we can also define blocks of code underneath a finally keyword that will always be executed whether a execution is raised or not. Important things to note here is that a best practice is to specify which exceptions are being caught. So we don't want to see what's referred to as a naked except here, meaning that the colon, that we just have an except with a colon, in which case any different error or exception that's raised from the code we're trying in Python will be caught here, and then we'll maybe handle that exception in the same way for all different errors. So we want to be careful with that and make sure that we're being explicit about the different kind of exceptions that we're willing to handle. Otherwise, we need to let them pass through to higher levels of the code. we can capture the exception itself to create more rich error messages, or do some inspection on the error. So here we have an example where maybe we have some strange OS error that's come up. We can capture that as E, getting the explicit instance of the exception, and then we can kind of interrogate it. So we can maybe print out custom error messages if the OS error is of a certain type that we're familiar with, so we can give either yourself or users more information about what kind of error they're experiencing. Class, this is just kind of a reference for a pretty complete definition of a class that we with all the critical pieces that we've covered in class on these things. So we have, in this case, we have a child class where we may be inheriting from some other class. It has class attributes, which are defined here at the same level as the methods. It has a constructor method that's always defined by this underscore init underscore. And just like any of the other class methods, the first argument to the class is going to be this self, indicating that the method requires an instance of the class to operate on. And so here we will set a couple of instance attributes, which remember are different from class attributes, where the class attributes can be accessed and are the same for any of the classes that we create. They're part of the class definition. Instance attributes will change based on the instance that we're working with. Here we're going to call this make complex val, where we do not have to pass self because we've decorated that as a static method. And I think that this is probably something I got the most questions about in the last quarter, was what kind of is the point of static methods. And the best explanation I can give here is that static methods are really useful in terms of associating a function, because this essentially acts just like a function that you could define completely separate from the class. But by making it a static method of the class, it ties it to the context of the class that it's associated with. So understanding that like this make complex val is very much associated, the operations in here are associated with the class, is really important because we can make it part of the class definition and tie it to that in the code. This becomes really important as code projects get really, really large, where if we were to find this function in a different file or above the class or below the class, it can be easy to forget that that's like really critical to this particular class that we need it for. And then finally we have class methods as well, which is really useful for creating alternate constructors for the class, where the first argument of these methods is the class definition that we want to, where we're going to create an instance of that class and return it. And the second thing is the arguments that we might, or additional data and arguments that we might need to generate that class. So often you'll see this in terms of like, we want to create a class from a file type that we store class information on. So maybe this would be something like in the vein of the homework examples that we've looked at so far in the quarter, it would be something like from CSV. We'd want to instantiate a class. And then we return that class instance by actually taking the data coming into that method and then sort of reorganizing it so we can actually call the class constructor appropriately. So things to remember: self always comes first in our class methods. So here, self always comes first. Static methods used for functions that are context specific and related to the class. And our class method is used to modify class attributes, is another good purpose for it, or to overload constructors. And again, this is mostly related to class attributes versus instance attributes, in that the instances of a class and the class definition itself are not the same.
Sorry to interrupt.
Yeah. Uh-huh. Sorry, was there a question?
Yeah.
Oh, sorry, it's very choppy. Can you try one more time?
It's in the message.
Oh, sorry. Thank you. The messages for midterm review?
No, it's in the message. It's Google Hangout.
Oh, the Google Hangouts. Gotcha. Thank you. Show messages. Cool. Good question. Let's see where. Okay, so here, the question was that we're calling. It appears that we're calling make complex value before we've actually defined it in the class. So that's a good question. In this case, we, as opposed to a compiled language where a compiler would read through these lines of code, go through here and find this function and come down to here and say, oh, okay, I have a function called make complex value. I need to find the symbol for that and figure out its operation so I can kind of make it part of this constructor method. Python will understand that at runtime it will try to look up this name and find that, but it doesn't need to be defined when we actually finish defining this class. So when we define the class, it'll go through and understand that like at some point it's going to look up that name when it executes the constructor, but it doesn't actually call it at the moment that we define the class. It's very similar to that example that we looked at here, where it doesn't complain, for example, if I just define this function where variable isn't actually a name, right? Like it's completely fine with that. But then when I try to call it, oh right, we've defined variable. Sorry. So let's call it something else, var. But when I actually try to call it, it's going to try to look up var at runtime as I've called the function, and it can't find it, and that's when it will throw the error, as opposed to when I'm defining that function. All right, good question. All right, a little bit on class inheritance. So here we have the syntax that we looked at before, where we have a child class, and then a parent class inside of there. And just remember that the method resolution order, in terms of how Python is going to try to look up methods on a class instance, it's going to check the child class. It'll then try to see if it's in the parent class, and then it's going to go all the way up into the object, right? I think if you were there for the lecture that I sat in for, or that I substituted for, I mentioned how everything in Python, even integers and floats and strings, all inherit from this object type. So it's going to go all the way up through the class hierarchy here, from the child class to the parent class to anything in between, all the way up to this object, and try to find the method on that object. Class attributes and methods can be overwritten in child classes. It's one of the benefits of polymorphism, so that we can create custom implementations for child classes. The super keyword allows us to access parent definition of different class attributes or methods. So here we have a fancy list, which is going to inherit from Python's list, and we're going to add this specific method that will only let us remove ints from the list. So when a value comes into this method, we'll check to make sure that the type is an integer, and then if it is, then we'll just call super.removeInt. Otherwise, we'll say, hey, this is a type error. So this is just an example, but in similar fashion, you could also call self.remove here in this case. All right. So that pretty much covers different pieces of material. Check messages. Okay. So in the notebook, which I will upload at the end of the lecture, There are also some examples of classes that you can kind of play around with, including ones with static methods. There's more examples of assignments and copying, and maybe this is worth running through real quick, just remembering that, like, if we have a nested list, or set of nested lists here that we declare with the name A, and then we say B is an alias for A, or is another name for A, and then we add something to A, B is also going to be modified here when we execute that line of code. And similarly, if we append to it, but if we actually change a value by looking at the first entry of the first list and setting that equal to 0, and then printing B, we see that we're going to have modified that first entry from 1 to 0 as well. And again, I keep harping on this, but it really matters that the ID of A and B are in fact the same. So there's more on this kind of as we go through here, and it's probably worth talking about pieces like this. So there's multiple different ways of creating copies of items in Python. So one of the ways that I often see people iterate over an object is something like this, where it's like, I want B to be everything that's in A. And so understanding what's going on there is important. Is that the same as before, as where we just said B equals A? Because this is essentially saying iterate over everything, so is it going to be the same in terms of the values and the object? And so here, if we define A as this set of nested lists, and then we use that syntax where we iterate over A and we assign it with the name B, if we do what we did before where we modify A and then look at B, we see in fact that B has not been modified. And so here we're actually creating a copy of that list A and handing it off to the name B. So when we modify A, we don't see a change in B anymore. And then down here, if we look at, similar to the example we were looking before, if we look at A is B, well, we know kind of by the fact that we modified A and it didn't change B that they're not the same object. But the first entry of A is the same object as the first entry of B. So here in this case, this is what's referred to as our shallow copy, where it's copied the outer container of this data structure, but not the interior. So that each value inside of that, inside of A and B is still the same object. So similar here. If we, and so this is a little bit funky too, right? If we do what we did before, so our append did not modify B, but if we index into the first entry, right, so our 1, 2 list of A, and we modify the first entry of that list, remembering what we just saw here, that list, that first list in A is the same as the one in B. If we modify that, we actually do see a change in B here. Not because we modified the outer list, which is B, but because we've modified this first inner object, which is the same between A and B. Here we'll do another method for copying A to B, and we'll see that, we'll take a look and see here, have we created a copy, and we see that the first print statement evaluates to false. So A is not B, so we actually have created a copy of A, but again, like we saw before, the first entry in A is the same object as the one in B. And here's yet another form where we did what we did before, and we copy, or we import this copy module, and we create a copy of A, and yet still the first object in that container is the same object, even though the containers themselves are not the same objects. And so finally we get into where we want to do this on multiple levels. We're going to create a deep copy using that copy module. And so we'll take A, we're going to create a deep copy that is B, and we'll see that A, our first print statement, A is not B, that is false. A is equal to B because we created a deep copy, right? That's kind of expected, and that would be true for any of these cases up here where we're making shallow copies as well. But down here, we see that our first entry in that list, or our first entry in that container that is a list, is not the same in A and B anymore. So if we were to do this operation where we make A of 0, right, so the first list in A and the first entry in that list, we're going to make it 0, and then we're going to print B, and let's print A just for memory's sake. If we do that, yeah, we've modified A already, so sorry. Let's do this. Okay. We've already modified A before to 0, so they were in fact the same. This statement was doing nothing in this case. So if we make a copy of A, and a deep copy of A, and provide it to B, but then we modify something in that first entry in A, then we're going to see the modification in A in that entry, but not in B. Whereas before, if we modified A, if we modified that entry in A, we did get a modification in B. So that's a sign that both this print statement here and also these 3 lines kind of give us evidence that the deep copy copies not only the outer container, but all of the containers inside as well in a recursive fashion. So I think that a student from a previous quarter said it well, that there are a lot of ways to make a shallow copy in Python and fewer ways to make a deep copy. So here we saw 3 or 4 different ways to make a shallow copy, and here only by explicitly using this module were we able to create a deep copy. So it's just something to keep in mind. And in terms of which is preferred, I would say that using the copy method here is very verbose. It's very explicit because you're saying I'm making a copy of this. This one's just not very clear because you're iterating over A, but there's no real indication that you're making a copy. That's just kind of a subtlety that you would need to keep track of. And I think that this last one is kind of a nice middle ground. I would say it's preferred. So even if A is a list to begin with, by calling list on it, it's pretty clear that we're making a new object and also what the name of that object is. Whereas these two, we just know that it's iterable, maybe. In this case anyways, we know that it's iterable. And here we just know that we're making a copy of some kind of object. We don't really know what we're getting out of it. So in the case where you want to make a shallow copy of a list, this is probably the best way to go. There's a little bit of info here on abstract base classes, and I'll leave that to you to look over if you'd like, or we can dive into it in the open discussion if we prefer. But that pretty much covers it for a review of our material from lecture. And so now I'll just kind of get into some of the pitfalls that are commonly encountered on these exams. Again, yeah, this is all the stuff that we just copied, but know your assignment conventions. So know whether or not you're dealing with the same object or the same value and the difference between those. Self always comes first in methods. That's a very common mistake we see in the parts where we ask you to write out code. And inside of those class methods, don't forget that when you're trying to access an attribute, just because you're inside of a class method, it doesn't mean you can just access attributes of the class. You need to provide this self dot attribute name to actually access the attributes of that class instance. That's kind of a hang up for people like me actually, who work with C++ a lot, where inside of those methods you can just call like a class attribute and the compiler will figure it out. The syntax here is very different, so making sure that you're using self.attribute to get attributes of that class instance. And as I mentioned before, with some of the range and enumerate and zip functions, built-ins are part of Python for a reason. They've become a standard because they're extremely useful in a lot of cases, and they keep us from writing our own versions of those with mistakes and multiple copies of them to keep track of. So it's worthwhile to kind of gain a little bit of breadth of knowledge in these built-in methods. They can really help you out. One that's not in the notes here, but I mentioned before again, is default dict is a really good one to have a handle on. Yeah, and everything. I would kind of just like page through the lectures and homework and see any of these. I think Paul does a really good job of being diligent about using the formatting in these slides. So if you see things from the built-ins, just kind of make yourself a little glossary of them, maybe, or the ones that you think you'd find really useful. So these are native types, but things like we discussed, like those functions for iterators, things like that. So one final tip is if you're in the coding sections where we're asking you to write lines of code and you can't recall the exact syntax for a statement, it's probably really handy to just go back and see. There may be a previous example in the exam itself where there's going to be formatted code blocks. You can see like, oh, that's how I can do my try except. I couldn't quite remember how to do that. So just check to see if one of those is in there, or maybe it'll spark some inspiration and help you recall what that's supposed to look like. So with that, that's pretty much all I have in terms of like structured review for the session. So we have another 40 minutes or so, and I'm just going to open the floor to any questions on Slack or on the Hangout. And we'll try to cover them as needed. But if you have other things to do this evening and you need to take off, don't feel obligated to stay. And it looks like the screencast has worked, so I'll be uploading that to YouTube along with the Jupyter notebook that we worked with. So yeah. Any questions?
Yeah. Hi.
Hi.
Could you just go over the static method and the class method that one more time? I'm still getting a little confused over that.
Sure. Yeah.
The static methods, yeah.
Yeah, for sure. Do you want to like see an example or?
Yeah. Like I mean, like the examples of where we could use it, and like it could help because I'm not getting the exact differences. I get confused over those two.
Sure. Okay. Yeah, let's dive in. I'm going to put this at the bottom. So, yeah, we'll use the employee, which is a pretty maybe overdone example, but we're going to create a class called employee. And the critical things that we want to know about employee is, or that we need to create a class of the employee in our constructor, is going to be their first name, their last name, their employee ID, and their middle name. Forget the middle name. Let's keep it simple. So when we create an employee, we're going to add some attributes. And we'll just call that ID. All right. So one other piece of information that we're going to want to know about our employees is their badge number. Okay, so their badge number is going to be combination of length of first name, length of last name, and their ID. Okay, so we could definitely just define this here. Right, so we'd want to do something like string of the length of their first name, last name length, right, and we'll convert both of those to strings, and then the badge number is going to be the integer of first name length plus the employee ID, which we'll assume is an integer. Okay, so this is all just fine in terms of like, readability and everything, but it kind of distracts from what we're actually trying to do in our constructor here. So like these lines of code. So typically one place where I've definitely seen static methods used is a place like this, where we have, based on the incoming pieces of information needed to create a class, we need to create some derived information. That derived information in our case being the length of this name, the length of the first name, the length of the last name, and the employee ID to create a badge number for this employee. So rather than have these extra lines in here, and this is a pretty short basic example, but I'm thinking of situations where this might be 10 to 15 to 20 lines of code. What we can do instead is say not self. We're going to create a new static method, which is going to do these pieces for us. And then here, and then inside of that, I should not pollute our namespace here. And then inside of that function, we can generate our badge number, and then in the constructor, this becomes a lot more clean. Okay, so that's kind of like, that's one example where I've seen static methods used before. Is just so that the lines of the constructor here are very simple. It's just gonna, instead of distracting from all of the different attributes that this class is going to contain by having a whole bunch of lines of code between here and there and having to scroll through it, we're going to put all of those lines into a static method so that our attributes of the class kind of come one after another in the constructor. Does that kind of cover it for static methods?
Yeah, that helps, yeah.
Okay, good. So for class methods, so let's go ahead and actually define this class. So for class methods, these are really useful in situations where we want to create a static, or sorry, we want to create a class using information that isn't like formatted in the way we need it. So for example, let's say like we have some CSV file and it's going to contain data which looks like this. It's going to have John Smith. I apologize if there's any John Smiths in the class. And it's going to have some employee ID associated with it. So this is just like a line in a CSV file. And so if we wanted to create an employee from this, we would do something like this. We would say first name equals data. Or maybe we would say, yeah, first name equals data dot split on commas, and give me the first entry. Here, give me the last entry, or sorry, not last entry, the next entry, and then for the final one, employee, let's call it just emp ID, data.split on commas, and give me the last entry, and then we're also going to make that an integer. And now we can create this employee class using that information. Maybe. Did I misspell something? Yeah. String, not into string. What did I miss here? In badge number, can only concatenate string. Oh, right. Sorry, in the badge number, our employee ID was still an integer, and it's not happy concatenating those together. So let's redefine that class. We'll rerun that cell to create John, and now we have John. So if we look at what all is in John, by using the built-in method dir, we're going to see some information like the badge number, the first name, the ID, the last name, which is great. But if we're going to do this in a CSV file, we're going to have to do this for every entry, which we'll probably throw into a loop. So maybe let's try it. Doing something like this. Oops. Lost a quote. Oh, right. This is not. Make sure I get my data structures right here. And then Patricia is going to have her own ID. And so then we'd say, you know, for employee data, we're going to do all of these things, right? We're going to create a first name, we're going to create a last name, and we're also going to just put this into a list of employees. So here, we'll just create some generic name E, and then in employees, we'll add that new employee to the list. Let me just look this over real quick. Let's say data here instead for a loop variable, so I don't have to make quite so many edits. All right, so we now have information representing like two different rows in a CSV file. We're going to create a list of employees. So we have for data and employee data. We're going to extract the first name, the last name, and the employee ID, create a new object, and then add that to employees with two E's. And we'll see what we get. List object has no ID split. Right. Okay, yeah, because I don't want these to be lists. Apologies. So my data structures right would help. Because these are just two different rows. They don't need to be lists as well. Okay, so when we rerun that, we're successful. And now if we look at employees, we see we have two different employee objects. Okay, great. So that's all gone pretty well, and probably looks fairly similar to some of the things we had to do in homework to parse things out of a CSV file. Okay, sorry, that was kind of a roundabout thing, but it's necessary to set up some context here for why we might want to use a class method to do some of this work instead. So here we're going to create a class method that is def from CSV line. So again, our first argument for a class method is going to be that CLS representing the class definition we're working with. And so here we're going to take in a line that is the CSV line, and we're going to do some of the work that we were doing down here in that method instead. So we'll go up here. Right, we're going to put that into our data. So we're going to kind of parse that line in this space, and then when we're done, we can simply return our class, providing the correct arguments, just like we did below in this line, because employee essentially is equivalent to our class definition that we're working with right now. Okay. So right now we're at a point where it's like, okay, well, we could do it in one place, we could do it in the other, but what's really the advantage of doing A versus B in either of these cases, right? So here we're going to start modifying this loop and removing a lot of verbosity from it in order to create these same classes. So I can basically get rid of those lines because we're doing them in the class method already. And instead of having to parse all of that out inside of a for loop, we can do that just by simply calling our class method from CSV line and passing it the data in that CSV line, ideally. Oh, right, I need to redefine the class above because I've added that method. And then execute that code, and we see that here, right? So now we've created this list. Cool, all right, so now we're at the same point we were. So what's the advantage, right? The advantage here is that those lines of code that we had in our for loop above will apply in other places. So let's say that we opened one file in this cell 72 here. In this space down here, we need to read another file. We need to read 10 more files, right? This code, these lines of code to create a class from a CSV line all exist here instead, and it becomes just as simple as calling that method anywhere else. In addition, now that we have this set up as a single call, right, and anywhere, kind of this is a nice opportunity to kind of point this out, but anywhere you see something like this, where you have creation of an object and then addition to a list, is probably a pretty good opportunity to move toward a comprehension. So sort of step by step, we can see like, all right, well, instead of assigning it a name, let's just add it straight to the list. We're just going to add new classes directly to our list without assigning a name in the for loop. And then really we're just like a quick hop away from doing something like so in our comprehension. Oops, just accidentally scrolled up, sorry. So we have our lines of data, we have our list comprehension. If we execute those two lines, we see we get the same thing, but now we've kind of placed all this execution in with the class definition. So it can be used anywhere, it's a lot less verbose, it's really handy in those ways. So, does that cover it?
Yeah, that really helped.
All right, good.
Yeah, that's good.
All right. Any other questions or curiosities? All right. Well, I'll hang around for another few minutes if anything comes up. But yeah, so I'll be here for a little bit, and then I'll cut off the stream and the screencast and all that stuff in a second. But yeah, a few more minutes. If anything comes to mind, feel free to jump on the chat or shout out.